Don't you mind that we record your presentation?
Yeah, that's okay.
Okay. So far we have 12 participants,
Okay,
but maybe we can start.
it's okay.
Okay, so it's a great pleasure for me to present Jari Taskinen from the University of Helsinki. He will give us a talk, Bergman Toeplitz operator on planar or periodic planar domains. Please, Jari.
Thank you very much. Thank you, Nikolai, for the invitation. It's a pleasure for me to be present virtually in your seminar and give this talk. So, as you see, the title is about Toeplitz operators on Bergman spaces. But the point is, very often, at least in one dimension, one is considering operators and spaces on the disk. But here the point is that, well, we have a domain in the complex plane. So, but it's still simply connected, but not a disk. It has the peculiarity that it is periodic, let's say, in one dimension, in the dimension of the real axis. I will put the things like that, and then on the other hand, in the other direction, it is bounded, so it is contained in a strip. This kind of domain, which is basically a union of infinitely many translated, bounded periodic cells, which I did not.
So you're dealing with upper half plane?
No, it's not upper half plane. It's a kind of subdomain of a strip.
Okay.
Okay, this is just a very brief abstract about the talk. So, okay, maybe I just directly go to see this picture. The domain looks like that.
Okay.
We have the real axis, imaginary axis, and this is periodic, as you see. So this periodic cell is here between the real coordinate -½ and 1/2, and this is one periodic in this real direction. So this set is repeating infinitely many times. It's simply connected union of these. So this is small pi0 or small pi in my notation, and let's go back to the abstract. So I have a Toeplitz operator in the full domain pi, and with symbol small a, and this is also assumed to be periodic. So if I take the restriction of the symbol to the periodic cell, then there appears the so-called Floquet parameter, and we have another actually family of Toeplitz type operators, but on a smaller domain. And I'm going to consider the relation of the spectra of these two things. And then there is a general band, spectral band formula, and then a more special construction where I take also into the game some thin geometric structures and can construct, I think, quite interesting examples of Toeplitz operators which have essential spectra with arbitrarily many disjoint components. This then, using the Riemann mapping method, can be turned in the Toeplitz operator just in the standard Bergman space in the disk with the same interesting spectral properties. Okay, the articles, it's in principle finished and submitted, but well, I thought it is a quite good article, and I sent it to the Duke Math Journal, but they didn't accept it, so it's being submitted. So standard notation in order to proceed. We have domain omega, which is this capital pi later in the complex plane, and then we have L2 space with respect to the real area measure, and the Bergman space is the closed subspace consisting of analytic functions. I will be very quick because I assume that the audience knows these things, because this is a talk in the Toeplitz operator seminar. So anyways, we have the orthogonal projection from L2 onto the Bergman space, denoted by P omega. Omega is the domain, and it can be expressed with the help of the Bergman kernel. And the Toeplitz operator, if we have a bounded function in the domain, then the Toeplitz operator is the composed of the multiplication with the symbol and the Bergman projection, and can be written with the help of the kernel with this integral formula. So I'm assuming that I don't need to pay more time for these. Then this is a repetition about the domain. So the periodic cell is this bounded set, which is contained, the real coordinate is, as I said, between in the interval from -half to half, and it's bounded in the other direction, in the imaginary direction, so contained in some such interval for some capital M. Then there are infinitely many translates of the cell. For each integer, we can make this translation, and the periodic domain is precisely the interior of the closures of the translates. So we get a connected set. There are some technical assumptions. I don't pay too much attention to these. They are rather mild. At least the domain should be with Lipschitz boundaries. Cusps are excluded from the boundary. And the boundary of the periodic cell is a Jordan curve, and polynomials form a dense subspace if we take the Bergman space in the periodic cell. Okay, this is once more the same picture. This is the periodic cell, and the whole thing is the full periodic domain, capital Pi. Now, this, what I'm talking about, is inspired by some very usual constructions in the theory of spectral elliptic problems, even Schrödinger operators, or spectral theory of the Laplacian, I mean in Sobolev spaces on periodic domains. So there they introduced the Floquet transform. I mean, when I mentioned the Schrödinger equation, even physicists know these things, and for them the Floquet transform is called the Bloch transform, and maybe in the Russian school of Sobolev function spaces, this transform is sometimes called the Gelfand transform, which is different than what many people understand by the Gelfand transform. But I call it Floquet transform. Floquet was a mathematician, Bloch was a physicist. And in this complex notation, it's a kind of similar to Fourier transform or Fourier series. So it acts, let's first put it act into capital L2 space. So we take a function f, and this is a linear operator which maps this function of the variable z in capital Pi into another function where we have z now not in the capital Pi but in the periodic cell, and then we have the Floquet parameter, which is like the Fourier parameter. Here, this capital I or boldface I is just this periodic interval from -pi to pi. So if you look at the right-hand side, it's a function of z and eta, although the original function was just a function of zeta. But here, as I said, zeta is z is in a smaller set, bounded set. Here it was in the beginning. The variable is in the full periodic unbounded domain. Okay, this all is very classical in the theory of unbounded operators in Hilbert spaces and Sobolev spaces. Namely, this mapping is it's actually unitary mapping from capital L2 onto this Bochner space, or vector valued capital L2. So we take the standard vector valued capital L2 space on the interval I with values on this L2 of small pi. So this is a unitary mapping onto. And so here this Bohner space, this is of course again a Hilbert space, and its norm can be indicated in that way. Well, all of that is basically just Fourier series, theory of Fourier series with this extra parameter z. So this can be, if without this z, this is just a Fourier series, and then the coefficients for a given function can be calculated, and this leads to a formula for the inverse Floquet transform. It has this concrete formula here.
Yeah, excuse me, one question. The image of your f, don't you take z from the pi naught initial cell, or it should run whole?
Okay, this is the pi naught. I mean, yeah, it is.
Yeah.
It's the same. I mean, I'm sorry, I'm using
Fundamental cell.
Yes, it's a periodic cell. Yeah.
Yeah.
Yes. Sure. Yeah. So we have these four functions in capital L2, and now next on this next slide, I just restrict the Floquet transform to the Bergman subspace.
Mm-hmm.
Then we are working with analytic functions, and of course this is just a restriction. It's still a nice isometric operator which preserves inner product, and the only question is about its range.
Mm-hmm.
And then of course the first idea would be to replace on the previous slide we had here capital L2 on the periodic cell. But if you just replace it by the Bergman space on the periodic cell, you get a too big space. It wouldn't be a mapping onto. And the reason is that basically these functions satisfy this kind of quasi-periodic boundary condition.
Mm-hmm.
Not precisely because, of course, Bergman functions don't have necessarily boundary values, but if you consider, well, take analytic functions on the periodic cell and find a dense subspace, maybe polynomials or maybe more general functions anyway, which have an extension to a neighborhood of that. And then you can set up this boundary, quasi-periodic boundary condition, and then you get the subspace of the Bergman space and take the closure of that subspace. You get something which is smaller than the full Bergman space, and this is my subspace A2 eta. Yes. Okay, and then when you take that, you get that Floquet transform is an isomorphism from the Bergman space onto that Bohner type space. Well, here this target or this space depends on eta, so this is actually not. It's a little bit more complicated thing, but anyway, it's a closed subspace of the original Bohner space, and well, that's how this can be made to work. Okay, now we have this Bergman type subspace, Bergman type space on the periodic cell. And if we had just a standard Bergman space, we would have the orthogonal projection, which would be the Bergman projection. We now still have the orthogonal projection onto this a little bit smaller subspace. And in my first paper, I proved certain things about that and proved that, well, it's a simple observation that this again has a kernel, this operator. So anyway, this p eta will be an important operator in the following. It's the orthogonal projection from L2 of the periodic cell onto this a little bit smaller Bergman type space. And now, once we have this for each eta, then we can proceed to the Bohner spaces. We had this bigger Bohner space, and then we have this smaller Bohner space. And if we take for each eta this projection, then we actually get an orthogonal projection from that Bohner space to this Bohner space where the values are analytic functions. And then there is a theorem, one of the main results in my first paper, which says that the original Bergman projection in the original periodic domain can be expressed in terms of this projection and the Floquet transform, quite natural formula. Okay, I'm not going to talk very much about this here. This is the stuff of my first paper, but now we proceed to Toeplitz operators. And in the next, I consider Toeplitz operators with bounded symbols, and I'm assuming that they have the same periodicity as the domain. So basically, once you know the analytic function on the periodic cell, then you know it everywhere. By this, I mean by this very simple relation. This is my assumption. Of course, such analytic function. No. I mean, I'm talking now about symbols, L infinity functions. So, of course, well, this is a very simple formula. We will consider such Toeplitz operators next. And okay, now recall that we have this Bergman type space on the periodic cell, and I'm going to define a Toeplitz type operator for each eta in this space in a natural way. Instead of the ordinary Bergman projection, I take it's necessary to take this orthogonal projection from L2 of small pi onto that space. And well, this is certainly kind of a Toeplitz operator, not a standard Toeplitz operator, but a Toeplitz type operator adapted to this present situation. All right, this is done for each eta. And now, so this is an operator in that space, but we can then proceed to the Bohner space by doing this for each eta separately. This is very natural, and then the following is an immediate consequence. I mean, the original Toeplitz operator with this periodic symbol can be obtained from this operator by applying the Floquet transform. Not a very big surprise. Anyway, but then we are about to proceed to the real stuff. Okay, on the previous slide, I considered these spaces A to eta on the periodic cell, and with the help of the original symbol, I defined these Toeplitz type operators in the smaller space. And I denote the spectrum of this by sigma Ta eta. So just the conventional spectrum of that operator. And the main theorem, the first main theorem of this study says that we have the following relation. The essential spectrum of the original Toeplitz operator in the periodic domain is the union of these spectra when eta is running over this interval I. And actually it happens to hold that the essential spectrum is the same as the full spectrum for this kind of operators.
In this case, you don't have compact operator with periodic symbols, yes?
Yeah, that's right. Because the symbol is periodic and there are infinitely many copies of this periodic cell, there cannot exist compact operators that type. Yeah, even if the restriction to one periodic cell is compact, but because we have infinitely many copies,
yes,
the operator cannot be compact. Okay, this formula is not completely my invention, of course, in this setting, yes, but this same formula appears in elliptic spectral problems, for example, for the Laplacian operator. It appears also even in theoretical physics and even in chemistry, quantum chemistry, because it appears for Schrödinger operators with periodic potentials. And one could talk a lot about that, but so I would like to say some words about the proof of this result a
Mhm.
little later. But now I go to the second thing. I'm going to introduce a little bit more geometry. I mean, as a special case of what I have presented above, and then produce some. I mean, I'm going to, well, I could say a little bit. I'm going to consider symbols such that if you take a restriction to the periodic cell, so the support of the symbol is a compact subset of the periodic cell.
Mhm.
So these operators would be compact. And then these spectra would be discrete. And I'm trying to organize the situation so that these spectra are close to each other for different eta. So they don't differ very much from each other. This can be obtained up to some extent. And now, since we have discrete spectra here, and all of them are not so far from each other, it will imply that that essential spectrum also could be it's not discrete, but it can have many disjoint components at least.
Mhm.
And this can be done with construction that I will show it very quickly. I will come to that very soon. It will be this kind of construction. This is still a periodic domain, but the point is here that there are thin ligaments, and the periodicity, quasi-periodic boundary condition is set up only here on the thin ligaments. And now I will play with this parameter and make it very small. So this means that this quasi-periodic boundary condition, it becomes less and less important because the area where it is set up is smaller and smaller. And then we come to a situation which I tried to describe. We have discrete spectra here, which are nearly the same for different eta, and then this would imply that this essential spectrum is disconnected. Okay. Now here is the result. I will probably try to draw a picture about that, but let's have a look at it first. So I'm claiming the following. Anyways, the spectra will be real because these Toeplitz operators will be self-adjoint. So if we are given any finite sequence of distinct real numbers, then I'm claiming that one can find a Toeplitz operator just with the bounded symbol on the disk, so that the essential spectrum of that operator intersects some small neighborhood of all of these points. And then the rest is a little bit more messy, but if you take the union of these disks denoted by U epsilon, then this is saying that the rest of the essential spectrum is at some distance from this union. Okay, let me draw this. I try to explain this here. I suppose you can now see something. So
yes.
This is the real just the set of real numbers. I'm drawing the spectrum here. Well, the spectrum is also a subset of the complex plane. Here are, so we have maybe 3 different given points, and unfortunately I cannot show my slide at the same time, but then we had these neighborhoods B, xn, epsilon. It's very terrible handwriting. And the theorem says that the essential spectrum of the operator intersects all of these. So I'm abbreviating, so these intersections are non-empty. And then U was the union of these sets. And then the rest of the essential spectrum was at some distance. At some distance of this set U. Well, which of course means that we have disjoint components of the essential spectrum. Actually, what I draw here is completely nonsensical, because as I said, the operator is actually self-adjoint, and what happens is that the rest of the essential spectrum is at least
these gaps.
Yeah, this is the zero, and so the essential spectrum actually consists of finitely many closed intervals. That's how the things will be in the reality. But okay, I should probably come back to the slides. All right. Okay, now I have at least explained what this theorem says. And before I proceed, I mentioned that so these components, which I said that they should be intervals. There are some finite number of intervals included in the real axis. And there are some quite deep questions which are partially unsolved in the field of spectral elliptic problems concerning these components. In principle, they could collapse into a set of discrete points, but the conjecture is that they really are intervals of positive length, because if there is a point, single separate point in the essential spectrum, that would be an eigenvalue of infinite multiplicity, and the conjecture is that they don't exist. And I'm sure the same is true also in the case of Toeplitz operators in this kind of examples. Also, there is another question, which is the so-called Bethe-Sommerfeld conjecture in theoretical physics, which says that in the case of Schrödinger operator, there can be only finitely many of these disjoint components in the essential spectrum, and probably the situation is also the same here. Okay, there could be some quite deep questions associated with these considerations, but I cannot go to that direction more. I don't know, but let's proceed with this approach. So what I said in the previous theorem was about the operator on the unit disk, but this is how my proof goes. So another formulation of a related theorem. It says that if we first fix a symbol on the disk, which is bounded and support is compact subset of the disk, then we have a Toeplitz operator just on the disk, and it's compact and its spectrum consists of real values. This is real valued, so the spectrum is a sequence converging to zero, like that. So the relation to the previous theorem is that now these numbers correspond to those given x's which were in the previous theorem. So I mean, given those x's in the previous theorem, one can always choose an operator such that these numbers coincide with those x's. So I proceed with this formulation. And then we have the same thing as on the previous slide, but for a Toeplitz operator in a suitable periodic domain. I mean, one can find a domain and a bounded Toeplitz operator with bounded symbol such that the essential spectrum intersects some neighborhoods of these points, and the rest of the essential spectrum is at some distance from the union of these points. Well, basically the same thing here, and the proof of this I can explain a little bit more, because well, I said something about the relation of this and the previous theorem. The other thing is that how can one go from this theorem to the previous one is to take a Riemann conformal mapping simply from, because this is a simply connected domain, and you take a Riemann conformal mapping from pi to the unit disk, and then you can get a nice Toeplitz operator with the similar properties on the unit disk. So this is basically, once one knows this theorem, one gets the previous one. And this I already showed to you. That's the construction of the domain and the operator. And it is a periodic domain, same periodicity as in the beginning of my talk. We start with a disk which has a radius a little bit smaller than 1/2. I mean R null. The radius is between 1/4 and 1/2, so it looks like that. And then we take this R was the radius of the ball where the support of the operator TB is contained. So I make a kind of a scaling here and get a symbol, the restriction of which to this first periodic cell is contained in a ball with radius like that. So this darker area contains the support of the symbol when it is restricted to the first disk or periodic cell. So, and this is done, I mean, in the same way in all of these periodic sets. So I have not denoted it, but the support of the symbol contains this, and it's similar in the other periodic cells. That's the definition of the symbol. And because there are infinitely many of them, you asked about that, but we get a Toeplitz operator which is certainly not compact. Okay, and then what? Then the things proceed more or less as I explained already. Let's see, what do I have here? We have this formula. And now these operators, the restriction of the symbol is a compact subset of the periodic cell. So these Toeplitz operators are compact. I mean, even though they are not completely standard Toeplitz operators, but one can show that they are compact, and so they are self-adjoint. So general theory shows that the spectrum is discrete. And then the main thing is that it is the operator is close, the spectrum is close to this operator TB, which was the given with which we started. And as I explained, when we diminish this geometric parameter, we make this ligament thinner and thinner. The part where this periodicity, quasi-periodic boundary condition is posed becomes smaller and smaller, and this is why these spectra don't depend so much on eta. To be a little bit more precise, we can fix any number, but finite number of the first highest eigenvalues for which this approximation is true. I mean, for which these first eigenvalues are nearly the same for all eta, and then from some point on we lose the control, and the rest of eigenvalues, they are smaller, but we cannot really control them. So I mean, we can get an example of an echelon spectrum where there are finitely many disjoint components. Yeah, this is what I would like to say about this proof at this point, but maybe I now go on drawing some more pictures and explain something more. So perhaps come back to this. Let's see, I first see if it is possible to do erase. Yeah, fine, this goes good. Not that much. I want to put it this way. So, okay. Right. Now it should work. Where is it? Here. Good. So maybe some more precise claims. One of the ingredients is in this proofs is the following lemma, the proof of which I think is something like 2 pages. So I take, there is a continuity with respect to this Floquet parameter. I take 2 values for the Floquet parameter, eta and mu. So I had this interval I, which is from -pi to pi. Then, okay. There holds that, now you remember we had this Bergman type projections, I mean orthogonal projections from L2 of small pi onto the Bergman type subspace. And we have this continuity that if we take the projection for 2 different parameter values, then these operator norms can be bounded by constant times square root of the absolute value of eta minus mu. And then this implies, you remember this related, I have now, this is for an arbitrary bounded periodic symbol. This implies the estimate also for the same estimate for the corresponding Toeplitz operators. And so these operator norms are in just as an operator from the Bergman space onto itself. And maybe a very simple explanation why one can prove such things is that if you take some Bergman function, maybe belonging, well, if you take any Bergman function in the periodic cell, then if you map with this simple multiplication, then you can change the quasi-periodic boundary condition. So if you, for example, assume that f satisfies the quasi-periodic boundary condition with parameter mu, then if you multiply by this, you can get it to satisfy the quasi-periodic boundary condition with parameter eta. So, and this mapping is not so bad. It's actually quite good. It's not unimodular because this is not real valued, but anyway, here one needs to the fact that the domain is bounded in the imaginary direction. Okay, this is one of the tools. I will refer to that quite soon. But one more remark about, I try to draw it here. So my symbol, I'm now talking about the last theorems. And here is the periodic domain, very beautiful one. Looks like that I'm a kind of 5 years old guy drawing his first pictures, but it is just because of this technique. So this was the periodic domain, and this is the support of the symbol. Now, and I said that using the Riemann mapping, you get similar spectral behavior for some Toeplitz operators on the disk. And now you would probably like to see something about how the symbols are on the disk. And well, if you apply Riemann mapping, I think the support of the symbol would be something like, that we have a kind of sequence of which comes to the boundary. And in principle, and two of them probably, because
in both directions.
Yeah, something like that. And this the restriction of the symbol, because it was periodic here, it's more or less the same on these. So it's a bounded symbol, but discontinuous. Of course, well, there is some constant value which appears, or many constant values which appear on all of these subsets. Well, this support is just disconnected, but you can, of course, add to this maybe some other, maybe positive symbol which goes to 0 on the boundary. And this is just a compact perturbation, and the essential spectrum would remain the same. So if you like, you would have a symbol which the support of which fills in the whole unit disk. So that is not a problem, but you cannot make the symbol continuous, of course, by such perturbations. Okay, so that's it. Okay, and maybe I still have some. So it's 60 minutes. Can I have 60 minutes, or how much time?
Yeah, you have. Yes, please. 15 minutes.
Yeah, very good. So then I'm just drawing here just a moment. I hope I got an empty sheet. Good. Now about this spectral band formula, that the essential spectrum of the Toeplitz operator is the union of the spectra of the operators in the periodic cell. I denoted this union by sigma. And so a sketch of the proof, of course, there are a lot of details that I'm not able to explain in 15 minutes or 10 minutes or whatsoever. But the proof to this direction, it was mentioned in the theorem that not only the essential spectrum is the same as this, but also the full spectrum is. So let's first try to see why this would hold. So this lemma A, which I mentioned on the previous slide, I mean, this continuity thing implies first, after some considerations of maybe one page, that this sigma set is closed. I mean, I'm a little bit worried, but probably you cannot just say that from general elementary topology, or can you? But okay, these are all closed, but this is an infinite union of closed subsets. I think you need some continuity thing in order to make the conclusion that the union is also closed.
But essential spectrum should always be closed.
Yeah, essential spectrum certainly, yeah, but yeah, of course,
Yeah.
but I'm trying to prove this.
Yeah.
I don't yet know that essential spectrum is the same as this.
Okay.
Yeah, so this thing first has to be proved. Then what next? I take lambda, which does not belong to sigma, and then okay, take lambda which does not belong to sigma. So what? Okay, so then it does not belong to any of these spectra. I can denote for all eta, R eta is the inverse of T A eta minus lambda identity. And it follows from previous fact, I mean, because the sigma is closed, that the operator norm of R eta is bounded. Okay, I'm sorry that my handwriting is so this is the operator norm of R eta. This is bounded by some constant C for all eta. Then one defines an operator R lambda, I mean in the Bochner space. So this was done, this is the operator, okay, I have to add here, it is the operator in A2 eta. And you remember the Bochner space was defined so that you take capital L2 on the interval and the values are here. So using that and this thing, you can define the resolvent R lambda in the Bochner space L2 I A2 eta. And well, this essentially needs this fact that we have a uniform boundary for these operator norms. And then it's not a big surprise, but you just Floquet transform. And this is the inverse of that operator in the original space, right? Okay, let's see. I am just, you don't see it, but I'm working here in order to get some more clean sheets. All right, so good. So I'm working with this identity. And the previous was something about the relation to one direction, and now this direction. So the idea is to construct a Weyl singular sequence, and maybe I have just enough time to explain more or less. So I have to show this inclusion, so I take an arbitrary lambda in sigma. This means sigma is the union of these, so I know about the lambda just that it belongs to the spectrum of one of these PAs. I denote it by the corresponding parameter eta by mu. Now this mu is fixed. Then I make a number of other definitions. So I'm defining, I will work in the Bochner space, and then I need a cutoff function. And Weyl sequence will, well, it's anyway an infinite sequence of functions, and this n is the index in the Weyl sequence eventually. But in order to define the nth element of the Weyl sequence, I first work with a little bit in the with the Floquet parameter. Define this kind of cutoff function. So this chi n is a mapping in the interval from -pi to pi, and has actually positive values. Then what else? Other ingredients. Now I'm assuming that lambda belongs to the spectrum of this Toeplitz operator. It could be, of course, this is a general formula, not for compact operators only, but for all Toeplitz operators. So this could be, for example, a point in the Ischenthal spectrum of that thing. It could be also an eigenvalue, very well. Anyway, because it may not be an eigenvalue, I just cannot pick up an eigenvector. But anyway, I can find a vector function g such that the value of the Toeplitz operator on G, or it maps it close to lambda G. This is the norm in the actually in A2 of small pi. This is one of the ingredients. Then, in order to construct, this was first thing here. Second thing is this, and third thing is I will need well, not quite a cutoff function, because you cannot unfortunately work with cutoff functions in the analytic world. I mean, it would be much easier in Sobolev spaces because there are cutoff functions. This is a function in the original Bergman space, and it has the property that if f is in the Bergman space, then this goes to 0 when n goes to infinity in the Bergman space. We have such things. Now I do again need one more, I hope.
What is the reason for that fact?
What?
What is the reason for that fact that it tends to zero?
Okay, let's see. Okay, let's see. Because this pi is approximately a strip in the direction of the real axis. No, well, yeah, when n goes to infinity, it means that the real part of this animal for a fixed z goes to plus infinity, and so it means that the real part of the exponent goes to minus infinity. Then we have that. Am I right?
Well, it seems that e to minus n square with fixed z goes to zero when n tends to infinity, because exponent decay very fast.
Yeah. So yeah. This the whole exponent goes to infinity.
Z on the exponent.
Z is fixed. Z is in the exponent. Yeah. My handwriting. Oh. Right, now another empty sheet. What else? This is nearly already the final Weyl sequence, not quite, because I still need some translations. Fn will be this approximating function phi n times gn, where capital Gn is the Floquet inverse transform of this chi n times g. And then the claim is that, okay, this is A. The claim is that we have this property if n is large enough. And then, well, I'm running out of time, but the Weyl sequence is made out of these fn's by translations in the direction of the real axis, because, well, fn, so this is in the Bochner space, we take Floquet inverse transform. So this is certainly in the original Bergman space on the periodic domain, and this is 2. So this is a function in the original Bergman space, and we can make the translations. So the Weyl sequence requires that the sequence must converge to 0 weakly, and this can be obtained by doing translations, because this function, it's nearly like a cutoff function. It makes that we can have a lot of space. So that side of the matters is quite clear. And we have a suitable normalization condition, which is also required in the Weyl sequence criterion. So the remaining thing is to prove this essential property. So then we get the Weyl sequence, and we have shown that lambda belongs to the essential spectrum of that operator. So now about this, we first note that Fn is an approximation of Gn, as was just we discussed on the previous slide. And then if I make the final calculation, Ta of Gn, so I can replace this Fn by Gn more or less. Well, then it is, I write the Toeplitz operator. If you remember, this was one of the formulas some time ago. Floquet transform, and then we have these Toeplitz type operators in the smaller spaces. And now we have this Gn. We have that, and so I cancel out these two Floquet transforms, It's terrible. And we get that. And the point was that this was eigenvalue corresponding to lambda in A2 of mu, not in A2 of eta. But this cutoff function in the eta variable was so that it is big when eta is close to mu, and it is null when eta is at some distance from mu. So this means that we can get an approximation that this whole thing is actually the Fourier, the Floquet transform of this function Gn, and this implies that formula. Okay. All right. So that's more or less the end of my talk. So this was my first experiment with this writing bad, and well, I will have to develop my technique a little bit more, but I hope I have been able to explain the results and some ideas of the proof. So I thank you for your attention. It was a pleasure to be present here in the seminar.
Thank you very much, Jari. Thank you. It was a very interesting talk, but can could you summarize in 2-3 very clever sentences, just to memorize for all of us, the main result you got?
Yeah. The first main result is this formula for the essential spectrum. I mean, of course, all of this is in this special situation that the domain is periodic, and the symbol of the essential of the Toeplitz operator has the same periodicity. The essential spectrum of the operator can be expressed in terms as a union of the spectra of these restrictions or modified Toeplitz operators on those Bergman type spaces. And the second result, well, going to more special geometric situations, it's a little bit technical formulation here, but the message is that one can find then, using these techniques, bounded Toeplitz operators with bounded symbols on the very basic Bergman Hilbert space on the disk, such that the essential spectrum is concentrated near this given set of real points on the real axis, plus some other component which is at some distance, and so this the essential spectrum of this Toeplitz operator has at least capital K disjoint components. I mean, here I should of course have mentioned the result by Sundberg and Cheng. It's 10 or a little bit more years old. This was the first, and as far as I understand, only example of a Toeplitz operator with a discontinuous essential spectrum. So this approach gives more examples and in some sense more systematic approach, of course.
So basically this result about separation of different parts of the spectrum.
Yes, yeah.
Okay, thank you. Thank you. Please, any questions, comments?
Nikolai, I have a question.
Yes, please.
Is there anything that can be said about the index? The Fredholm index.
Well, you know, am I right or not? If your spectrum separated in disjoint components, contractible components, that index should be 0.
Yeah, but in this general situation, yeah, but I don't. Maybe these operators are so special. If you have a periodic symbol, maybe it's far from being Fredholm. Yeah, I did not think it's anyway. It's a good point. One should relate Fredholm theory to this also. I don't know if there is a relation, but thanks for I think for this question. Yeah.
Yeah, I have maybe a related question is to do with the boundary, because you said that you have this quite nice boundary. Is that because of the use of the Riemann mapping theorem, or is there some other reason that also?
I need polynomial approximation here at least. It did not show up in the proofs.
Right.
Yes, I don't know if the Fredholm property has much to do with the boundary. This I don't see.
Right. Just maybe one more question, because some of the motivation or ideas relate to the spectral problems in elliptic problems, and
yes,
do they compute does the index play any role there, or is it computing in those considerations?
Usually there one wants that the problem is solvable, and one wishes to have a unique solution, and then of course then one wants that the operators certainly are Fredholm. But then in the spectral problem, yeah, this is usually very relevant to talk about the Fredholm properties, but on the other hand, they may be clear from other considerations, and so maybe this Floquet theory is I don't remember that this is exactly used for proving anything about for Fredholm properties. Yeah, this is probably treated with other methods.
Okay, thank you. I might talk more.
Other question or comments?
I have just a trivial remark, a simple remark about your first theorem. Yes. Could you please show the Fourier operator, Floquet operator?
A Floquet operator, yeah. Okay, yeah, this. Do you mean this?
We don't see your slides.
Could you please show it again?
Okay, yeah. I have to share the screen, of course. It's so complicated now.
Yeah.
Well, just you work with Toeplitz operators with shift invariant symbols, and my trivial remark is that you could work with all shift invariant operators and simplify them. So instead of the C-star algebra and Toeplitz operators, one could work with the von Neumann algebra with the centralizer of the translations. Well, it is just a simple extension.
Yes, okay, thank you. Actually, I have been thinking of doing this not just for Toeplitz operators, but also for it. Thanks for this suggestion. Yeah.
Of course, the interesting part is the analysis of the spectrum, the approximation, all that thing. Yeah.
Yes. Yeah. I could not really go into the depth of these proofs. Of course, well, the proofs altogether are something like 10 pages. So yeah, it would require a little bit more time, more work to explain everything.
Okay. If no more questions or comments, Jari, thank you very much again for your nice talk. And once you will have new results, you are very welcome to present them.
Okay. Okay, thank you once more for the invitation. It was a pleasure, and I hope really to see you at least online, or maybe next year sometime. I don't know.
Sometimes, somewhere, yes.
Yes, indeed. Okay, thank you.
Okay, great. Kevin, are you here?
Sure.